times the normal force. Force of friction is always proportional to whatever is pressing up against it. The harder you press against something, the harder it is to move. And that mu tells you how scratchy those two surfaces are. That's the coefficient of friction. So force of friction equals coefficient of friction times normal force. Now, some of the shortcuts here. Remember, weight and force of gravity mean the same thing. So if they give you weight, that's the exact same thing as saying force of gravity. Mass times gravity. And we can use a shortcut. Instead of 9.8, we can use 10. Just like we've been doing in class. Secondly, normal force. Normal force is typically opposite to gravity. So through our Newton's first law, since they're opposite, that means they should be equal, right? But don't forget, if there's an angle between them, you got to throw in that cosine of the angle. Remember, cosine gives you which axis? The x-axis. So again, this is a shortcut here. Throw in the cosine of the angle, and that's going to give you your normal force. All right. Anytime you work with force problems, always draw a free body diagram. Label it. That's going to help you to keep all the forces in order. That's going to help you to visualize which forces are opposite, and that's going to help you to set up your Newton's first and second law problems. When we deal with Newton's first law, remember, the sum of the forces is the sum of all the forces. Remember to put in the signs for directions. So if it's down or to the left, it's negative. If it's up or to the right, it's positive. Remember, you need to do this for the x and for the y. And then you can use your vector equations in order to resolve this into its result. For Newton's second law, yes, force equals mass times acceleration. But remember, there's different iterations of this. If I'm talking net force, I'm talking the object's acceleration. If I'm talking the force of gravity, I'm talking the acceleration due to gravity. If I'm talking centripetal force, I'm talking centripetal acceleration. Notice how the force and the acceleration always match. So that means whatever direction the force is in, the acceleration is going to be in the same direction. So make sure that when you go to solve these, if you're using Newton's second law, you're always matching the correct acceleration with the correct force. All right, any questions about our forces?
No, sir.
All right. So our next topic is work, energy, and power. So one of the biggest things here is the definition of work. Work is force times displacement force times displacement, but only the amount of displacement that happens the same direction as the force. You must have displacement to do work. So what examples can you think of where work could never happen?
You pick the box up and then move gravel in the box. Kind of like you pick up the box and you just back up.
Pick up the box and back up. because you're applying a force up, but the displacement is going to the left. So nothing's in the same direction. What else? If I move like that, did I move?
Yes.
Did I undergo any displacement? What's the definition of displacement?
Change distance.
A change in position. Did I change position?
No. You were back.
So, did I undergo any change in displacement?
No.
Did I do any work?
No.
By definition, I did not. So work is force over a displacement. So anytime you're talking circular motion, you cannot do work in circular motion. Work is always going to be zero because you're always returning to the same position. Work is proportional to kinetic energy. Remember, our law of conservation of energy says energy cannot be created or destroyed, it can only be altered in form. So if my kinetic energy changes for any reason, that energy doesn't go away, it gets converted into work. Just like our kinematics. If I have a force versus displacement graph, well, what quantity here is going to give me the amount of work?
The area.
The area. Because remember, area
Space times time.
is base times height. And force times displacement is work. When we undergo our change in kinetic energy, we can actually use work to find out what our velocity is. Because work is the change in kinetic energy. If I'm at a zero velocity to start, that means zero velocity or zero kinetic energy. I can actually use the work in order to calculate what my kinetic energy is afterwards. And our kinetic energy is 1/2 mass times velocity squared. The other part of that energy is going to be our potential energy, which is given by mass times gravity times height. And what's our value for gravity?
-10.
-10 meters per second squared. Now, we also said that our law of conservation of mass says energy cannot be created or destroyed, only altered in form. So how would we mathematically describe that?
KE equals PE.
My initial energies have to equal my final energies. So, whatever my initial kinetic energy, my initial potential energy, and my work is should be what my final values are. Any questions about energy? I mean, these, again, are fairly straightforward. The only issue that you will have with this is, again, they won't just ask you a straight energy equation. They will ask you a force equation and ask you if work was done. They will give you velocity, and they will ask you how potential energy changed. They'll give you a height and ask you how much work was done. So they're going to use this in particular to see if you understand conservation of energy. They will also use kinematic equations and force equations to see if you understand this. Because remember, height is another way of saying displacement. Velocity so they can throw in kinematic equations. Here we have nu Newton's first or second law equations. So they're going to incorporate a lot of these things and have you have a string of equations to come up with an answer. Our last thing here is power. And power is just how much work is done over time. So remember, work is changing kinetic energy. So really it's any energy over time. Well, if power is work over time, and work is force times displacement, I can reword this as force times velocity. And they will use either one of these interchangeably. So if they're asking about power, they may give you force and velocity. They may give you work and time. So make sure you're comfortable with either one of those. All right, any questions about our work, energy, and power? All right. Next topic is our momentum. And what is momentum? It is a movement.
It's mass times velocity.
It's how much velocity does it take to move a mass. Momentum and inertia are used interchangeably because it's, well, how do I get something to move? So we end up with P equals mv. And that's our momentum equals mass times velocity equation. But momentum by itself really isn't useful because we're not so much concerned about getting an object moving. We're concerned with collisions. What happens when that object hits something else or something changes its momentum. So we have this other term called impulse, which is given by that italic I. That's our change in momentum. So if momentum is mass times velocity, and impulse is our change in momentum, that would mean impulse is change in mass times velocity, or mass times change in velocity. Well, we know from our kinematic equation that velocity is acceleration times time, and mass times acceleration is force.
Yeah.
So another way that I can write impulse instead of mass times my change in velocity is force times time. Again, these are interchangeable. If they tell you impulse, that's just a change in momentum. So that's just telling you if this hits that, well, this momentum changed. It gave an impulse to this, which changed its momentum. Just like our law of conservation of energy, we have law of conservation of momentum. What does conservation mean again?
It changes to another form.
It changes to another form. So that means my initial momentum has to equal my final momentum, especially when you're talking about multiple objects. So initial momentum of 1 plus initial momentum of 2 has to equal the final momentum of 1 plus the final momentum of 2. Momentum is a vector quantity as well. Most of the problems that you will see will be linear, so there won't be any angle between the two of them. So this equation is going to be good enough. But just be aware that if they do give you an angled momentum, So if this hits at this angle, and this object is going this way, where is this object going to go? So now I'm only concerned with the amount of x momentum, the momentum that's going in the same direction. So that means we need our trig functions and our Pythagorean theorem. So we're going to use the same idea as we did with force by resolving it into our x and y components. We're going to handle the x momentum, we're going to handle the y momentums, and then we're going to use our tangent and our Pythagorean theorem in order to find our result. All right, any questions about momentum? All right, why don't we take a quick break here.